So today we have a very beautiful geometrical problem. We take a right angle triangle. Now inside this right angle triangle, we inscribe a rectangle. Now as we have inscribed a rectangle inside this right angle triangle, due to this situation, two more right angle triangles are formed. One is over here and the other one is over here. So first of all, we inscribe a circle in the top right angle triangle so that the circle is tangent to all the three sides of this triangle. In the similar way, we inscribe a circle in this bottom right angle triangle, and this circle is also tangent to all the three sides of the triangle. Now take the biggest right angle triangle and inscribe a circle inside it so that the circle is tangent to all the three sides of this triangle. Now because of this particular arrangement, there is a very beautiful relation between the radius of these three circles. So if we take the radius of this blue circle as a variable x, the radius of the pink circle as a variable y, and the radius of this yellow circle as a variable z, then the relation is x plus y equals to z. In simple words, the radius of the bigger circle is equals to the sum of the radius of the other two smaller circles. So this is Anmol, and now let us see the solution. How can we prove the relation between the radius? Okay, now let us start with the solution. So before we move on to this actual proof, let us understand a very beautiful relation between the circle and a right angle triangle. So suppose the arrangement between a right angle triangle and circle is like this way. There's a right angle triangle with the side lengths as equals to ABC. So here we have the right angle triangle. Now let the height of this triangle be A, the length of the base be equals to B, and the length of the hypotenuse be equals to C. Okay. Now inside this right angle triangle, you inscribe a circle in such a way that the circle is tangent to all the three sides of this triangle. So because of this arrangement, there comes a very beautiful relation between the radius of this circle and the side lengths of this triangle. Okay, now what I'm thinking is to not give you the direct relation between the radius of the circle and the side lengths of this triangle. Instead, let me show you a proof, and at the end of the proof, you will eventually come to know about the relation. Okay, so first of all, it was a given data that this particular circle is tangent to all the three sides of this right angle triangle. So the first thing that I will do is I will simply draw the radius to all these three tangent points. So before that, let us mark the center of the circle. Okay, now we can see that the circle is tangent to this side of this triangle at this particular point. So if I will simply draw the radius to this particular point, the angle formed over there would be 90 degree. And this is because of the theorem, the angle formed at the point of contact between the radius and the tangent line is always 90 degree. Okay. Now we can see that again the circle is tangent to base of this right angle triangle at this particular point. So I will again draw the radius to this particular point, and again the angle formed over there would be 90 degree because of the same theorem. Now we can see that the circle is also tangent to this side of the triangle. So again I will draw the radius to this particular point where it is tangent, and again the angle formed over there would be 90 degree. Okay, now what I will do is I will take the radius of this circle, something like a variable r. Okay, so all these three yellow line segments are ultimately the radius of the circle, hence they will have the length as equals to r. Okay, so now we can see that in this particular quadrilateral, out of the four angles, three of the angles are 90 degree. Hence by applying the angle sum property, the value of the fourth angle, that is this particular one, will also turn out to be 90 degree. So now we can see that in this particular quadrilateral, all the four angles are 90 degree and adjacent sides are equal. Hence, this particular quadrilateral is a square of side length equals to r. Okay, why r? Because it is the side length of these adjacent sides that were equal. Okay, now look carefully. The length from this perpendicular point to this particular point is b because it is the base of this right angle triangle. The length from the perpendicular to this particular perpendicular is equals to r. Therefore, the length of the remaining line segment, that is from this perpendicular to this particular point, will turn out to be the longer length minus the shorter length. Hence, it will turn out to be simply b minus r. So the length from this perpendicular to this angle is simply b minus r. Similarly over here, the length from the top angle to this perpendicular is a, that is the height of this right angle triangle. The length from this perpendicular to this perpendicular is r. Therefore the length of the remaining line segment, that is from this top point to this perpendicular, will simply turn out to be the longer length minus the shorter length. So the longer is a, the shorter is r. Therefore the remaining length will have a length a minus r. Now look carefully. What I will do is I will draw a line segment joining the center of this circle to this particular point. So now what we can see is that this particular right angle triangle and this right angle triangle are congruent to each other because of right angle hypotenuse side. We have these right angles, the common hypotenuse, and the two sides that are equal between these two triangles are these yellow color line segments that are ultimately the radius of the same circle. Rest of the things between them become equal. So if this side of this right angle triangle has a length b minus r, therefore that side would also have a length b minus r, and it is going to be from this perpendicular to this particular corner. Okay, so let me write that thing very nicely. So the length from this perpendicular to this corner is simply going to be b minus r. Okay, the same thing will happen over here. I will simply draw a line segment joining the center of the circle to that angle. So we can see that this triangle and this triangle would be congruent to each other again by right angle hypotenuse side. So if two triangles are congruent, rest of the things between them become equal. So if this length is a minus r, the length from this point to this perpendicular will also turn out to be a minus r. Okay, now look carefully. It was given that the length of the hypotenuse is equals to c. So the length of the hypotenuse is from a to b. For example, let me just label this thing. So this point is a, this point is b, and this middle point where it is perpendicular, let it be equals to p. So we can see that AB is equals to C. Now AB can also be written as AP plus PB, okay, and that is equals to C. Now the length of AP is A minus R plus the length of PB is B minus R, and this thing would be equals to C. Now we need to simplify this equation in order to isolate R. So first of all, on the left hand side we will have A plus B minus 2R equals to C. I will subtract C on both of the side and add 2R on both of the side. So on the left hand side I will have A plus B minus C, and this thing is equals to 2R, and at the end we will get the value of R as equals to A plus B minus C divided by 2. So here we can see that we have got the value of the radius of this circle in terms of the side length of this triangle. The original diagram was like this way. If we have a right angle triangle of side lengths A, B and C, and inside this if you have a circle that is tangent to all the three sides of this triangle having a radius r, then the value of r is simply equals to a plus b minus c upon 2. Okay, so now we need to mark some of the lengths inside this diagram. Now the theorem that we just saw, in that we can see we required the radius of this circle in terms of variable and the side lengths of the triangle. So here three circles are present and their radius are already taken as variables. Well and good. Now we need to take the side lengths of the triangle as variable. Now just wait a minute. Before we mark the length of the line segment as variable, let us mark some of the angle. So first of all, this angle would be 90 degree because it is the right angle triangle. First of all, this biggest right angle triangle. Now this angle would be 90 degree because it is the corner of the rectangle. Similarly this one and similarly this one. Now as this line is a straight line, by linear pair that angle would also be 90 degree. Similarly over here, as this line is a straight line, due to linear pair this angle would be 90 degree. Okay. Now what I will do is I will take the length of this rectangle as a variable p. Now we are going to take the height of this rectangle, or we can say the breadth of this rectangle, as a variable q. Okay. Now the length from here to here I will just take it as a variable a. Now what can you say about the length from here to here? So look carefully, it is again the breadth of the rectangle, hence it would again have a length equals to q. Similarly, this length from here to here is simply the length of this rectangle, and that we have already taken as a variable p, hence it would also have a length p. Okay, so here we can see that because of this rectangle, some of the lengths got equals to each other, and this thing is going to play an important role in our solution. So now let us take the length of the remaining line segments as variable. So the length from here to here we are going to take it as a variable b, the length from here to here as a variable c, and the length from here to here as a variable d. Okay. Now look carefully in this particular right angle triangle. So I'm just going to redraw this right angle triangle outside the diagram so everything is clear. So the right angle triangle is present over here, and the right angle triangle is like this way. Okay, the height of this right angle triangle is having a length q, the base of this right angle triangle is having a length a, and the hypotenuse of this right angle triangle is having a length d. Okay, now inside this right angle triangle we have this pink circle whose radius in terms of variable has been taken as y. Now recall this theorem. According to that particular theorem, the radius of the circle would simply turn out to be a plus q, that is the addition of the lengths of the height and the base. Now from this we need to subtract the length of the hypotenuse, therefore minus d, and all of this divided by 2. So here we have got the value of y in terms of a, q and d, that is ultimately the radius of the circle in terms of the side length of the triangle. Now let us take the other right angle triangle in which we have a circle, and that is present on the top. The blue circle is very nicely placed inside this particular right angle triangle. So the right angle triangle that we have now is like this way. We have the right angle triangle. Inside this right angle triangle we have this circle whose radius in terms of variable has been taken as x. The height of this right angle triangle we have taken as a variable b. the base of this right angle triangle is having a length p and the value of the hypotenuse is equals to c. So according to the above discussed theorem, the value of x will simply turn out to be b plus p minus c divided by 2. Okay. Now let us take the third circle and the third right angle triangle, and this one is the biggest right angle triangle that is inscribing the yellow circle. So the biggest right angle triangle is like this, and inside this we have the yellow circle that is tangent to all the three sides. Okay. Now what can you say about the height of this right angle triangle? So this thing is simply going to be b plus q. So the height of this right angle triangle is b plus q. Now the value of the base will turn out to be p plus a. So we are going to write it as a plus p, and the value of the hypotenuse will turn out to be c plus d. Okay. And now the radius of this circle in terms of variable has been taken as z. So according to the theorem, the value of z will turn out to be the addition of the lengths of the height and the base. Therefore b plus q, that is the height, plus a plus p, that is the base, minus the length of the hypotenuse, that is c plus d, and all of this divided by 2. So here we can see that we have got the value of z in terms of all the variables that were present in the diagram except the radius. Now what we are going to do is we are going to just rearrange some of the terms present in the numerator. Z is equals to, so now what I will do is, first of all I will take this positive a, then I will take this positive q, and then I will take the negative d. Look carefully, it is negative c plus d, so if I will open the brackets, the term will turn out to be negative c negative d. So I have taken the terms a, q, and now I will take negative d. So these three terms I will just write it together. Now this thing added with, now I will take positive b, positive p, and negative c together. So b plus p minus c, and all of this thing was divided by 2. Now we can just separate out the 2 with each of this bracket. So the thing will turn out to be a plus q minus d divided by 2 plus b plus p minus c divided by 2. Now look carefully to the two equations that we have got previously, the one in the pink color and the other one in the blue color. So first of all, the pink equation gives us the value of a plus q minus d upon 2 as equals to y. Now look carefully over here. What we have is a plus q minus d upon 2. So this thing is ultimately having a value y. Similarly, look at this other term, that is b plus p minus c upon 2 is equals to x. So ultimately the value of this term will turn out to be x. So now we can see that the value of z can now be written as y plus x. And this is the relation between the radius of these three circles that we were looking to prove. So this was my way to prove this particular relation between the radius of these three circles. If you have any other method other than this, or else if you have any other question that you think I should try, you can do comment below. And if you want to share any kind of picture related to a solution or a problem, you can email me, or else you can send it to me on my Instagram. The link is in the description.